Hello, my name is Stephen Girvin. I'm a professor of physics and professor of applied physics at Yale University and a member of the Yale Quantum Institute. I'm going to talk to you today about quantum computing, about circuit QED, which is the primary architecture for building a quantum computer using an all-electronic system of superconducting quantum bits. It was developed here at Yale with my colleagues Michel Devereux and Rob Sholkoff, and I'm going to introduce you to that topic and then talk about quantum error correction, how you can try to do nearly perfect calculations on a quantum computer built from imperfect parts. The first quantum revolution was in the first half of the 20th century. It brought us the transistor, the laser, the atomic clock, the global positioning system. And the inventors of quantum mechanics were doing basic research. They did not foresee these remarkable quantum devices. The inventors of these quantum devices did not foresee their amazing applications that brought us the technological revolution of the 20th century, that the first makers of individual handmade transistors could not imagine integrated circuits, and the fact that today in the world, approximately 60 trillion transistors are produced every second. These quantum devices, however, from the 20th century do not actually take advantage of the full power of quantum mechanics. There's now, in the 21st century, a second quantum revolution, which is building devices to take full advantage of the full power of quantum mechanics. And one of the powers has to do with computing, processing information in completely new ways. Quantum computers use the principle of superposition, that a quantum bit or qubit can exist in an infinite number of states that are intermediate between 0 and 1. There is some very crude sense in which quantum bits can be both 0 and 1 at the same time. A more subtle concept is that of entanglement. And entanglement is another kind of superposition that allows there to be non-classical, extra strong correlations amongst different bits that are widely separated from each other, something that Einstein objected to strongly because he understood the implications of this new quantum theory. He called it spooky action at a distance and did not like it. These two effects, however, give us a kind of quantum parallelism that lets a quantum computer do many calculations in parallel and at a rate which is impossible on any conventional computer. The irony is that as part of a daily routine engineering calibration test of our quantum computers, we carry out these spooky operations that Einstein felt had to be impossible. And we use those to verify that our quantum computer really is a quantum computer and not a classical computer. So now that you are experts on quantum computing, here's a quiz, but don't worry, I'm going to give you the answers. The first question in the quiz is quantum information carried by waves or particles? And the answer, of course, is yes. Second question, is quantum information analog or digital? And again, the answer is yes. Quantum information can be stored in a continuous analog fashion in intermediate superpositions between 0 and 1, and yet when we measure the quantum bit, we always get the result 0 or 1. So now let's talk about circuit quantum electrodynamics, the idea of quantum electrical circuits, quantum integrated chips. The experiments I'm going to talk about are carried out by my colleagues Michel Devereux, Luigi Frunzio, Rob Sholkoff, and there are many graduate students and postdocs on both the theory and experiment side that have contributed to the ideas that I'm going to tell you about. So what is quantum electrodynamics? That's the study of atoms and electrons coupled to photons, to particles of light. And the fact that the electromagnetic field is quantized means that it has zero-point fluctuations or vacuum fluctuations, quantum uncertainty in how big the electric and magnetic fields are even in a vacuum when there's no light, supposedly. And these fluctuations modify the spectrum of atoms, of the energy levels of atoms. So for example, if I have a hydrogen atom, the first thing you learn is there are certain quantized energy levels which are stationary states that live forever. But if you look more closely, if you include the fact that this atom is sitting in the electromagnetic vacuum, which has fluctuating, those fluctuations will destabilize the 2p state and cause the electron to fall down to the ground state, the 1s state, irreversibly by spontaneously emitting a photon into the vacuum in a typical time of about 1.6 nanoseconds. Other effects of vacuum fluctuations in which an electron can virtually emit and then quickly reabsorb a photon leads to an effect called the Lamb shift, which causes the 2s and 2p states to not quite be at exactly the same energy. The goal of cavity quantum electrodynamics is to modify the available photon states by, for example, trapping atoms between two highly reflecting mirrors that reflect optical light that can interact with the atoms and make, instead of a continuous range of photon frequencies available to the atom, only discrete allowed resonances based on the distance between the two mirrors in the cavity. I'm going to talk to you about microwave cavity QED, or circuit quantum electrodynamics, in which we have some sort of superconducting box or other resonator in an electrical circuit which completely surrounds a region and can trap microwave photons inside. So it's like having almost perfectly reflecting mirrors completely surrounding an artificial atom, which I'll tell you about. And unlike the optical cavity QED case, the atom, when it tries to emit a photon in any direction, it's always reflected back and is not able to escape. And as a result of that, the lifetime for spontaneous emission of the excited state of our artificial atom can be enhanced by a factor of 1,000 if the cavity does not have a resonance frequency that matches that of the atom. And this enhancement of the lifetime is very, very helpful in trying to store and manipulate quantum information in superposition states of our artificial atoms. So in circuit QED, which is an analog of cavity QED, as I said, the microwave photons are inside superconducting circuits, and we don't use real atoms, we use artificial atoms, Josephson Junction quantum bits or qubits. And these artificial atoms are very large and couple very strongly to photons and give us the ability to do what's called nonlinear quantum optics in a completely new regime of individual photons. So here you see a cartoon of a hydrogen atom, obviously not to scale. The diameter of the Bohr orbit is about 10 to the minus 10 meters. The frequency of transition between the 1s and 2p state that I talked about is about 2.5 petahertz, 10 to the 15 hertz. The lifetime of the excited state before it spontaneously decays, as I mentioned, about 1.6 nanoseconds. The Q of this oscillation, the quality factor, which is the product of the frequency and the lifetime, is about 4 million. And the transition dipole moment, the ability of this atom to couple to electromagnetic fields because there is a charge moving around, is captured by this so-called dipole moment, which is about 1 dBi, or about 1 electron charge times the Bohr radius of this orbit. Let's compare this to an artificial atom made of superconducting aluminum evaporated on an insulating substrate and containing a Josephson junction, which I'll explain momentarily. The size of this atom is about a millimeter. It's 7 orders of magnitude larger than this atom. It has a transition frequency 6 orders of magnitude smaller, about 7 gigahertz, which is in the domain of cell phone signals, microwave signals. The lifetime of the excited state is about 300 microseconds, much longer than the hydrogen atom. But the Q, the quality factor, is about the same, 2 million. But what's really different is the transition dipole moment, which is sort of a measure of how much charge is moving over what distance. That's several pairs of electrons moving a millimeter. It's about 30 million times larger than for the hydrogen atom. And this enormous transition dipole moment allows us to do quantum mechanics and quantum electrodynamics in a completely new regime. So this object, this Josephson junction object, can be an artificial atom. It can be viewed as a quantum bit or qubit. It has to be operated near absolute zero so that the metal is superconducting. But you can build superconducting integrated circuits out of this by the same technology that's used to make semiconducting integrated circuits in today's classical computers. The transistor of quantum computing, the heart of our artificial atom, is this thing called a Josephson junction, which I mentioned before. It consists of 2 pieces of aluminum, which are superconducting, separated by a very thin 1 nanometer thick insulating layer of aluminum oxide. Here you see an electron micrograph of it. It's about 2,000 atoms wide and 2,000 atoms high and a few atoms thick. This object provides the anharmonic energy structure of an LC oscillator. It acts like the artificial atom has a capacitor and it has some nonlinear inductance caused by this Josephson junction, which allows pairs, so-called Cooper pairs of electrons in the superconductor to tunnel through this thin barrier and slosh back and forth between the 2 capacitor plates on this artificial atom. And it acts like an inductor whose inductance is not constant but varies with how much current is flowing in the circuit and makes this into an anharmonic oscillator. The potential seen by this oscillator is a cosine of a certain angle, a certain phase difference of the superconducting order parameter across the 2 sides of the junction. Here's a different design, the so-called Transman qubit. This is like an artificial atom with atomic number 1 trillion. It has 10 to the 12 mobile electrons in these aluminum films evaporated on this insulating substrate. It's like an antenna, a millimeter long, and the two halves of the antenna are connected by this Josephson tunnel junction. You might think if I had an atom with atomic number 10 to the 12, it would be impossible to solve for the spectrum of that atom. It would be impossibly complex. But superconductivity gaps out all of the single particle excitations in the electron gas, in the aluminum, and the only low energy excitations are pairs of electrons sloshing back and forth between the two antenna pads. And so the quantized energy levels of this object are simply those of an anharmonic oscillator. The ground to first excited state transition is at perhaps 5 gigahertz, and the first excited to second excited transition is at perhaps 4.9 gigahertz. Slightly lower because the cosine potential is softer than the parabola of a harmonic oscillator, and so it has negative anharmonicity. The quality factor of this is, as I mentioned, about the same as a hydrogen 1s2p. But the enormous transition dipole moment caused by the charges moving back and forth a millimeter means that this atom, which has its own antenna built in, can talk very, very strongly, couple very strongly to microwave photons in a cavity which is surrounding this artificial atom. So this is the artificial atom in our circuit quantum electrodynamics. What can we do with this? Well, here is an example. Here is a Hamiltonian. You don't need to understand the details, but there's a mode in the cavity, which is a harmonic oscillator. It has an energy, which is an integer times Planck's constant times the frequency of the resonator. This just counts the number of photons in the microwave cavity. We can approximate the two-level atom, the anharmonic oscillator as a two-level atom and describe that mathematically as a pseudo spin a half, with spin down being the ground state, spin up being the excited state, and because the other transition frequencies are different due to the anharmonicity, we can ignore them in a certain approximation. And when the atom and the cavity have different transition frequencies, then the net effect is you are in what's called the dispersive regime, and the effective dipole coupling enters in second order and produces this term, which causes the transition frequency of the atom to shift by a number chi each time you add one more photon to the cavity. So here you see the spectrum of the cavity, of the atom. We shine microwaves on the atom and see what frequency causes it to transition from the ground to excited state. And we see a series of peaks corresponding to how many photons are in the cavity. 0, 1, 2, 3, 4, 5, 6, 7, 8 microwave photons in the cavity. Chi is negative, so the frequency goes down. There's a quantized light shift associated with how many photons are in the cavity. So what you should learn from the fact that there are discrete peaks here is that microwaves, despite their name, are particles. They are photons. They're just as good photons as the optical photons that cause the chemical reactions in your eye that let you see, even though they have 100,000 or 1,000,000 times less energy. They're still particles with quantized lumps of energy. And the fact that you now can detect these individual microwave photons is giving us new ways to search for certain types of dark matter called axion particles. And so one of the applications of all this is not simply to produce a new kind of quantum computer, but also to do quantum sensing, to detect extremely weak signals of interest in cosmology and astrophysics. So with this Hamiltonian, with this strong coupling between the atom and the cavity, we can control the state of both. We can apply drive signals to the cavity shown here. We can apply drive signals to this Transman two-level system here and produce any quantum state of the combined system. For example, suppose we wanted to do something that would be considered extremely difficult in ordinary quantum optics. Take an empty cavity with 0 photons and put exactly 6 photons into that cavity. That would be extremely difficult with ordinary optics, but is relatively easy here. So here you see a plot of some control signals that have been pre-computed that we apply to the Transman, and another control signal that we apply to the cavity. And here is a graph where the color scale shows you the probability that there are n photons in the cavity as a function of time. And you see you start at 0, it rises up, it dips down, it kind of splits into 2 parts, and then at the last second, or the last nanosecond, 500 nanoseconds into the sequence, boom, all of the probability lands on n equals 6. There are now exactly 6 photons in the cavity. And here you see a plot called the Vigna function, which verifies for us that we are in the n equals 6 state. So you can think of this Vigna function as a kind of quasi-probability distribution in the phase space of the quantum oscillator. So think of this axis as the coordinate of the electromagnetic oscillator. Perhaps the electric field measured at the center of the cavity would be the coordinate. And this axis is the momentum, or the magnetic field, in the electromagnetic oscillator. And you see this beautiful bullseye pattern, which is completely circularly symmetric and changes color. The colors indicate the sign of the Vigna function. So it's not a probability distribution, it's a quasi-probability distribution like a quantum amplitude, because it can be both positive and negative. The fact that it's completely circularly symmetric means that we don't know the phase of the oscillation of the cavity, and that's just the number-phase uncertainty relation. We know that the number of photons is exactly 6, so we cannot assign a phase to that. It's a superposition of all possible phases. Here's another example. We can create Schrödinger cat state. We can make an oscillator be displaced to the right and to the left to be in 2 coordinates at the 2 different places at the same time. And here you see the Vigna function for that case. You see this blob on the left represents the coherent state minus alpha. We've displaced the oscillator to the left. This blob represents the coherent state plus alpha. The oscillator is displaced to the right. You see that it's a blob, not a point, as it would be classically, and that's vacuum noise. That's the fact that the position of the oscillator and the momentum do not commute. And so it's impossible to know both of them precisely simultaneously. Equivalently, this is the vacuum noise, the electromagnetic noise of the vacuum right before your very eyes. In the middle, you see what we call the whiskers of the cat, these very rapid sine oscillations of the Vigna function. And they can be used for quantum sensing. If you displace the oscillator very, very slightly in the momentum direction, you get a very strong change in that signal, even though the displacement is much smaller than the 0-point uncertainty in the momentum. Furthermore, the fact that the central fringe is the same color as the blobs tells us that we have an even cat, a plus sign in the superposition of being here and being here, and not a random mixture. So not an incoherent mixture, a true Schrödinger cat with a coherent superposition with a definite sign between coherent displacement to the left and to the right. Just to give you some icing on the cake, here is a kind of Schrödinger cat living in 35 places at once. This is an amazing recent experiment from my colleague Michel Devoret, in which he has made a so-called Gottesman-Kitaev-Preskal state, which is very powerful for quantum error correction. And you see these blobs, which are actually squeezed now. They're smaller than the uncertainty in the previous slide, and the cat is in 35 different places in phase space at the same time. So that just demonstrates for you the level of quantum control that we have over these quantum states. Okay, so now that's the hardware, the background. Now I want to talk to you about the quantum error correction problem. How do I correct errors in a quantum computer that has imperfect parts? So here is the problem in a nutshell. I'm going to give you an unknown quantum state. If you were to measure it, it will collapse. It will change randomly due to this back action resulting from your measurement. That's a problem because if this unknown state develops an error, I want you to fix it. It seems impossible, but miraculously it can be done. The fact that in principle quantum error correction is possible is to me much more profound and amazing than the fact that you can do quantum computation in principle with a perfect device. You can now even do it with real devices that are imperfect. It's still extremely challenging, but I will show you experimental progress that we are now able to do this at some level. So how does quantum error correction work? How can you get around the fact that when you examine a quantum object, you change it? So what you need to do is store the quantum information not in one physical qubit, but in a logical qubit consisting of many physical qubits. In this example, there are 9. And you store the quantum information, the superposition of ground and excited state, not in one physical object, but in these spread out in some non-local, non-classical, spooky action at a distance kind of correlations among all of these qubits. And the non-locality of putting the information in there is very important because you need for it to be true that no single physical qubit can know the state of the logical qubit, of the information you're trying to store. Because if that one qubit develops an error or is measured by the environment, which is what decoherence is, then you do not want the environment to learn the state of the logical qubit and collapse its state. So you need to hide the information from the environment. But then you need a Maxwell daemon to correct those errors when they occur. And the Maxwell daemon, which is itself made of imperfect parts, has to be so fast and so accurate that it can make certain clever measurements which do not tell it the state of the logical qubit, but do tell it what errors may have occurred and on which of the 9 physical qubits the error occurred, so that it can be corrected and the entropy, so to speak, pumped into a cold bath to keep this logical state pure. Well, there's a big problem right off the bat that when you have n physical qubits, the error rate has suddenly become n times worse because each one of the physical qubits can have independent errors. So every quantum error correction protocol starts by taking a giant step backward and making the error rate worse. Then you have to turn on a very clever Maxwell daemon that is so fast and so efficient and so accurate and doesn't introduce errors of its own that will overcome this factor of n and get you back to the break-even point where the quantum information lives as long as if it had been in one of the single physical qubits. And hopefully, even better than that. You want to be much longer lifetime than just reaching the break-even point. So it turns out that all previous attempts to overcome this factor of n and reach the break-even point of quantum error correction have actually failed. And the reason is that the Maxwell daemon has to figure out all the different errors that could have occurred, a bit flip, a phase flip, a combination of both, and which of the n physical qubits suffered that error. So it has to make many, many clever measurements of so-called error syndromes, which tell it about what errors may have occurred, but do not tell it about the logical state in which the error occurred. So that's quite complex and difficult. It's been attempted, it sort of works, but it never actually makes things better by overcoming that factor of n. It always makes things worse. So we want to try a different idea, which is not to use material objects as quantum bits, not those artificial atoms that I showed you, but use microwave photon states stored in high quality factor superconducting resonators as our logical qubit. And so to compare, let's just consider the case of 3 physical qubits, just to keep it simple. Each is a 2-level artificial atom. It has a total of 8 states in the combination of 3. And the states can be represented by the binary numbers 000 through 111. So there are 8 numbers there. And each of those 8 quantum states can have some quantum amplitude in the entangled correlated state of the logical qubit. Instead of that, which is complicated because, again, there are many errors that can occur and we have to figure out which physical qubit had the error. Instead of that, let's think of putting microwave photons inside a cavity, and there can be 0 photons, 1, 2, 3, 4, 5, 6, or 7. So there's a total of 8 states we'll consider. And they can have exactly the same quantum amplitudes as are stored in these 3 physical qubits. And it's a continuous variable system. It's described by some wave function, psi of x. It's just a harmonic oscillator. X is the coordinate of the oscillator. But in that continuous variable system, we have a discrete basis of photon number states, and we can store exactly the same information. But it's on one physical object, a cavity, containing photons. And that's simplification, using a single object that has many states in its Hilbert space instead of many objects with only 2 in each of their states, is the simplification. So why is that an improvement? Well, this harmonic oscillator has one mode and it's weakly damped, very, very weakly damped. It's a high Q oscillator, and it has only one kind of error. It can decay by losing a photon. And you don't need to know which of the modes or which of the physical qubits lost the energy. It's just one single mode with one possible error. So if we could think of a thing to measure that would detect that error. We only have to measure that one thing. And it turns out for us, again, something that's very difficult to measure in ordinary quantum optics, but easy in circuit QED, is the photon number parity. Is the photon number even or odd? And if I see the photon number change from even to odd, I know that I have lost a photon, an error has occurred, and I need to correct it. So here is the simplest so-called bosonic code, or continuous variable quantum error correction code, that I know of, which we developed a few years ago here at Yale. This is the binomial code, or the kitten code. It's a whole family of codes, but the simplest version is the following. The zero logical state is a coherent superposition of 0 photons in the resonator plus 4 photons in the resonator. The one logical state is 2 photons in the resonator. So it's very simple. If I should lose a photon, which happens when the lowering operator A gets applied to the state, then 0 logical has now 3 photons in the state, and 1 logical in the error state has 1 photon. And this is very efficient. It uses only 5 photon states, or log 2 5 bits. It uses fewer states than the corresponding discrete variable error correcting codes, because it has fewer errors. And the recovery that I want to apply when I know that the parity has jumped, I should emphasize that these two code words are both eigenstates of parity. They're both even photon numbers. And the error words have odd photon numbers. So when I see the parity jump, I have to apply a unitary operation that maps 3 back to 0 plus 4 and 1 back to 2. Well, those are non-trivial, tricky operations that would be very difficult in ordinary quantum optics, but turn out to be relatively easy with our universal control in circuit QED. So I won't go into the details, but here are some experimental results from the Luyan Sun group in Tsinghua doing quantum error correction on this code and improving the lifetime by applying the error correction and reaching 92% of the break-even point, so almost reaching break-even. And the first code, and so far the only code, which has actually exceeded break-even and was done slightly before that experiment, was done here at Yale in the group of my colleague Rob Sholkoff, and it used a superposition of 2 different Schrödinger cat states. Remember, the Schrödinger cat state, let's say for the 0 logical, is oscillator displaced to the left, superposed with oscillator displaced to the right. 1 logical is the oscillator displaced in positive momentum, superposed with displacement to negative momentum. And the Vigna functions of those 2 code words are shown here. And you can produce, with our universal control, arbitrary superpositions of those states. And the properties of these states are very favorable for quantum error correction. And by encoding the information in these logical photon states and applying the error correction operation, the Sholkoff group, for the first time in any technology, finally exceeded the break-even point, only about 10%, but did so. And then it turns out that this system will raise its hand when there's an error. It will herald errors. And in 20% of the cases, it raises its hand and says something went wrong. If you post-select only on the 80% of the data where that didn't happen, then you reached 1.75 times break-even. So this is still not as good as we want to do, but it's the first time that break-even has been robustly reached. So we have a great staircase to climb towards our ultimate goal of fault-tolerant quantum computation. And you can see a series of steps here. We're somewhere in the middle. We've created a logical memory with a slightly longer lifetime than the individual physical parts through quantum error correction. We've done operations on single logical qubits. We've done entangling gates on pairs of logical qubits, but we're still a long way from error correction producing dramatic enhancements of the lifetime and being able to do that at large scale to produce a full fault-tolerant quantum computation. But we feel like we're making great progress and doing lots of interesting physics along the way. So here, thank you very much for listening. And here are some references to the experiment and theoretical papers. Thank you very much.